Welcome to the Deep Dive. Today we're tackling something that really shapes the world around us, but maybe doesn't get the spotlight it deserves.
Right.
We're talking about Flux-Cored Arc Welding. FCAW. It sounds technical, I know, but it was a huge step forward in how things get built, especially out in the field on site.
Exactly, and that's our goal today, isn't it? To really get under the hood of FCAW. We want to unpack how it works, what makes it different, and why it's just so versatile. We're pulling all this from a really detailed source we've got called FCAW, FCAW.pdf.
Okay, let's unpack that. So the source mentions its development mid-1980s as a major step for successful on-site semi-automatic welding. What did that actually mean for the people doing the work? How did it, change the game, enabling different materials, different conditions?
Well, it really comes down to the wire itself, the core idea, literally. See, unlike your standard solid wire, FCAW wire is like a tiny metal tube. And inside, it's packed with this granular flux. That design, that's what gave welders so much more freedom. Think about welding high up on a building frame, outdoors, maybe it's windy. Before FCW, that was incredibly difficult, maybe impossible, with semi-automatic methods. This opened up, whole new ways to build big things efficiently on location. And the Flux, it can hold elements you'd normally find in like stick welding electrodes, MMA electrodes, so it makes it useful for a much wider range of jobs.
Right, that versatility. And one thing that really jumps out is that the flux itself can create the shielding gas. So it doesn't need that separate bulky gas cylinder all the time.
Yeah.
Why is that independence so important, especially out in the fields where, regular MIG or mag welding might struggle?
Oh, that self-shielding. It's a total game changer, especially outdoors. Like you said, conventional MIG-Mag uses an external gas shield. A bit of wind, poof, it's gone. Your weld quality suffers. With self-shielded FCAW, the gas is generated right at the arc, inside the flux core, so it's much, much more tolerant of drafts and wind. It honestly means you can keep working in conditions that would just shut down other processes. And speaking of the wire, it's really crucial that the seam on that tube is good, mechanically sound, hermetically sealed, because if it's damaged or just poorly made, moisture gets in. And unlike some things, you can't just bake these wires to fix them once they're contaminated. It doesn't work.
Okay, so the self-shielding is huge.
Yeah.
But you mentioned the flux does more. It sounds like it's doing a lot inside that tiny core. What else is this flux actually achieving for the welder beyond just the gas cover?
Yeah, it's pretty clever stuff. Multifaceted, really. So yes, it helps make the gas cover, making it better in drafts than the solid wire. But it also forms a slag. This slag layer covers the hot weld metal as it cools, protecting it from the air. And crucially, that slag layer provides support. It helps hold the molten weld pool in place when you're welding out of position, like overhead or vertically.
I see. So it stops it dripping everywhere.
Exactly. Anyone who's tried to weld overhead knows the frustration.
Yeah.
That slag support is a massive help for getting a good weld in awkward spots. Plus, you can put alloying elements in the flux.
Right.
So you can tailor the weld metal's properties, make it stronger, tougher, whatever you need. And one more technical bit, because the wire is hollow, the current flows through a smaller cross-section of metal. This increases electrical resistance, which actually helps increase the burn-off rate at any given current.
Yeah.
Makes it more efficient in a way.
It's amazing how much chemistry and physics is packed into that wire.
Yep.
You mentioned alloying elements. If we look at the list in the source,
Yeah.
what are things like, say, aluminium doing in there, or manganese?
Good question. So aluminium and manganese, they're primarily in there as deoxidizers and denitrifiers. Basically, they help clean up the molten weld pool. They react with oxygen and nitrogen, pulling those impurities out to form slag, leaving you with cleaner, sounder weld metal. Stronger, less prone to defects.
Okay, like little scavengers.
Sort of, yeah. Then you've got something like nickel. Nickel's added for toughness, strength, hardness, and also corrosion resistance. Really boosts the weld's overall robustness. And then there are elements like potassium and sodium. Their job is more about the arc itself. They help stabilize it, make it smoother, and they contribute to forming that slag we talked about. Silicon's in there too, often working alongside manganese as a deoxidizer, and it also helps form slag. It's this carefully balanced recipe inside the core.
Got it. So we've touched on MIG-Mag before, solid wire, external gas. How does FCAW stack up against it in terms of, how you actually use it? What are the key operational differences a welder would notice?
Right. There are some definite distinctions. Operationally, FCAW usually runs on DCEP, direct current electrode positive, though some of the self-shielded wires actually run DC in, electrode negative. A really big difference is the metal transfer mode. FCAW generally doesn't use what's called dip transfer.
Dip transfer. That's common in MIG, right? Where the wire touches a puddle.
Exactly. The wire dips into the pool, causes a short circuit, melts off, reignites the arc. It works, but it can sometimes lead to issues like lack of fusion, especially if the settings aren't perfect. FCAW typically uses spray transfer or globular transfer, which avoids that dipping, so it tends to be less prone to that specific lack of fusion problem.
Mm-hmm.
Equipment-wise, you need different feed rolls for FCAW.
Knurled ones.
Knurled, like with teeth. Yeah, precisely. To grip the softer, hollow wire properly without crushing it. Smooth rolls used for solid MIG wire wouldn't work well. And the self-shielded wires often use a slightly different torch design. No need for a gas nozzle in the same way. Oh, and some specialized FCAW wires, like for hard facing, can be quite large diameter. They might need a pretty hefty power source to run properly.
Okay, so different setup, different operating characteristics.
Yeah.
But what does that translate to in terms of advantages?
Yeah.
What are the big wins for choosing FCAW on a project?
Well, the advantages are pretty significant, which is why it's so popular. First off, productivity. It's fast. You can lay down a lot of weld metal quickly. The source mentions up to 10 kilos an hour, which is impressive.
Wow.
It's got great all-position capability. Welders generally find it gives good control over the weld pool, especially the rutile type wires. And interestingly, the source notes that these rutile wires can match the mechanical properties and low hydrogen levels of the basic types now, which is quite an advancement. Compared to, say, stick welding, MMA, you can use a smaller groove angle for your joints, which saves time in filler metal. The bead appearance is usually very smooth, with less risk of undercut at the edges. Basic type FCAW wires are known for producing welds with excellent toughness, really good for critical structures. And as we discussed, the ease of adding alloys via the flux means there's a huge range of specialized consumables available. And of course, the big one for many applications, the self-shielded option. No external gas needed for some wires. That's huge for site work.
It definitely sounds like a powerful process. But nothing's perfect, right? Every tool has its downsides. What are the limitations or disadvantages people need to keep in mind with FCAW?
True, there are trade-offs. Firstly, it's mostly limited to welding steels and some nickel-based alloys. You don't really see it used on aluminum or copper, for example. And unlike MIG, which can sometimes produce almost no slag, FCAW always produces a slag covering because of the flux. And that slag has to be chipped or brushed off after welding.
Ah, an extra step.
Exactly. Adds time and labor. Also, the wire itself is generally more expensive, kilogram for kilogram, than solid MIG wire.
Okay.
Now, you might make that back in productivity, so the overall cost might be lower, but the upfront wire cost is higher. And while the self-shielded wires are great in wind, the gas-shielded FCAW wires, they can still be affected by drafts, much like MIG-MAG. You still need to be careful outdoors with those. Finally, it tends to produce more welding fume than MIG-MAG does. So fume extraction and ventilation are even more critical considerations for welder safety.
Okay, that makes sense. Let's dive even deeper right into the wire construction itself. The source talks about different ways these cord wires are actually made. What's the job of the outer metal sheath and the powder inside? And how do the manufacturing methods affect how the wire performs?
All right, this is interesting stuff. So that outer metallic sheath, its job is basically to hold everything together, give the wire its shape and stability so it feeds properly. It also carries the welding current, of course. And it plays a role in stabilizing the arc. The powder inside, the flux core, well, that's doing all the things we talked about. Adding alloys, producing the shielding gas, forming the slag, sometimes adding iron powder to increase deposition rates. Now, how they make the wire tube has a big impact. The source describes a few types. You've got seamless cored wire. As the name suggests, it's a solid tube filled with flux, no seam.
Okay.
Big advantage. It's not sensitive to picking up moisture. You can often copper coat it too, which helps with current transfer. And it usually has a thick sheath, so it feeds well, even with simpler two-roll drive systems. The downside, it's apparently difficult and more expensive to manufacture. Then there's butt joint cord wire. Here, the edges of the metal strip forming the tube meet edge to edge. It's also pretty good against moisture and can be copper-coated, thick sheath too. But getting that butt joint perfectly sealed seems to be the tricky part during manufacturing. And the last one mentioned is overlapping cord wire. This apparently the easiest to make. The edges of the strip overlap to form the tube.
But there's always a but.
Yeah, the but is significant. It's much more sensitive to moisture getting in through that overlapped seam. If it gets damp, it's basically ruined. You also can't copper coat it easily, and the sheath tends to be thinner, which might require more careful feeder setup.
So the way it's made directly impacts things like moisture resistance.
Yeah.
That's crucial for reliability on site, isn't it?
Absolutely. Choosing between, say, an overlapping wire and a seamless one isn't just about the initial price tag. It's about performance consistency, especially if you're working in damp or humid environments or if storage isn't perfectly controlled. That moisture sensitivity is a really practical consequence of the manufacturing choice.
Yeah, that really crystallizes it. FCAW is such a prime example, isn't it? How a seemingly small change in material science, putting the flux inside the wire, created this huge leap in welding capability, giving us that high productivity, that versatility, especially for those really challenging, tough environments. It literally changed how we build things.
It really did. And it makes you wonder, looking forward, if you think about all those different functions of the flux elements we discussed and these distinct wire manufacturing methods, where does the innovation go next? How might tweaking the composition of that core or refining the production techniques further push the boundaries? Could we see FCAW tackling even more complex materials or being used reliably in even more remote or extreme applications? What new possibilities might open up? It's quite something to think about.